Hello, everybody. In this episode, I'll be speaking with Stephen Casper. Stephen was previously an intern working with me at UC Berkeley, but is now a PhD student at MIT, working with Dylan Hadfield-Manel on Adversaries and Interpretability in machine learning. We'll be talking about his Engineer's Interpretability sequence of blog posts, as well as his paper on benchmarking whether interpretability tools can find Trojan horses inside neural networks. For links to what we're discussing, you can check the description of this episode, and you can review the transcript at axrp.net. All right, welcome to the podcast.
Thanks, good to be here.
Yeah, so from your published work, it seems like you're really interested in neural network interpretability. Why is that?
One part of the answer is kind of like boring and unremarkable. It's that lots of people are interested in interpretability, and I have some past experience doing this. And as a result, it's become very natural and like easy for me to continue to work on what I've gathered interest in and what I have some experience in. You definitely know that from when we worked together on this. But aside from
Yep.
what I've just come to become interested in, interpretability is interesting for a reason to so many people. It's part of most general agendas for making very like safe AI for all of the reasons people typically talk about. So I feel good to be working on something that is, generally pretty well recognized as being important.
Can you give us a sense of why people think that it would be important for making safe AI, and especially like to the degree that you like agree with those claims? I'm interested in hearing why.
Yeah, I think there are a few levels in which interpretability can be useful. And some of these don't even include typical AI safety motivations. For example, you could use interpretability tools to determine legal accountability, and that's great, but it's probably not going to be the kind of thing that saves us all someday. From an AI safety perspective, I think interpretability is just kind of good in general for finding bugs and guiding the fixing of these bugs. There's kind of like two sides of the coin, diagnostics and debugging. And I think interpretability has a broad appeal for this type of use. Usually when neural systems are evaluated in machine learning, it's using some type of test set and maybe some other easy evals on top of this. This is very standard. And just because a network is able to pass a test set or do well on some sort of like eval environment or set, that doesn't really mean it's doing great. Sometimes this can actually actively reinforce lots of the biases or problems that we don't want systems to have, things like dataset biases, right? So, at its most basic, interpretability tools give us this additional way to like go in and look at systems and evaluate them and look for signs that they are or aren't doing what they want. And interpretability tools are not unique in general for this, right? Like any other approach to working with or evaluating or editing models, is closely related to this. But one very, very nice, at least like theoretically useful thing about interpretability tools is that they could be used for finding and characterizing potentially dangerous behaviors from models on very anomalous inputs, right? Think like Trojans, think like deceptive alignment. There might be cases in which some sort of system is misaligned, but it's almost impossible to find that through some sort of normal means, through treating the model as some type of black box. And interpretability is one of a small, unique set of approaches that could be used for really kind of characterizing those types of particularly insidious problems.
Okay, so it sounds like your take about interpretability is it's about like finding and fixing bugs in models. Is that basically right?
I think so. And lots of other people will have like contrasting motivations. Many people, more than I, will emphasize the usefulness of interpretability for just kind of making basic discoveries about networks, understanding them more at a fundamental level. And I'll never argue that this is like not useful. I'll just say I don't emphasize it as much. But of course, like engineers in the real world benefit from, theoretical work or exploratory work all the time as well, even if it's indirect.
Yeah, I mean, I'm wondering, like, why don't you emphasize it as much? It seems potentially like, I think somebody might think, okay, we're like dealing with AI. We have these neural networks. We're maybe going to rely on them to do like really important stuff. Just like developing a science of what's actually going on in them seems potentially like it could be pretty useful and potentially like the kind of thing that interpretability could be good for.
Yeah, I think there are maybe I kind of have three mini answers to this question. One is if we're on short timelines, if highly impactful AI systems might come very soon, and we might want interpretability tools to be able to evaluate and understand as much as we can about them, then we want to have a lot of people working on engineering applications. The second
Hmm.
mini answer, I think, involves just pulling in the right direction, right? It's not that we should have all engineering relevant interpretability research, and it's not that we should have all basic science interpretability research. Like, we probably want some sort of mix, some sort of compromise between these things. That seems very uncontroversial. But right now, I think that the lion's share of interpretability research in the AI safety space is kind of focused on basic understanding as opposed to the engineering applications. So I think it's kind of useful to pull closer toward the middle. I think
Hmm.
the third reason to like emphasize engineering applications is to like make progress or get good progress signals for like whether or not the field is moving somewhere. Because right, if a lot of time is spent kind of like speculating or pontificating or basically exploring what neural networks are doing, this can be very valuable, but only very indirectly, and it's not clear until you apply that knowledge whether or not it was very useful, right? So using things like benchmarking and real world applications, it's much easier to get signals, even if they're kind of somewhat muddled or sometimes not perfectly clear, about whether progress is being made than it is if you're just kind of exploring.
Okay. Before I really delve into some things you've written, one question I have is like, if I want to be kind of fixing things with models or noticing problems or something, I think one version of that looks like I have a model that I've trained and now I'm going to do interpretability to it. But like you could also imagine an approach that looks more like, oh, we're going to like really understand the theory of deep learning and really understand like on these data sets, like this learning method is going to do this kind of thing that ends up looking less like interpreting a thing you have and more just like kind of understanding what kinds of things are going to happen in deep learning, just like in general. I'm wondering, like, yeah, what do you think about that alternative to interpretability work?
Yeah, so it definitely seems like this could be the case. We might be able to like mine really, really good insights from the work that we do, and then use those insights to like guide a much richer understanding of AI or deep learning that we can then
Hmm.
use very usefully for something like AI safety or alignment applications. I have no argument in theory for why we should never expect this, but I think empirically,
Hmm.
there are some reasons to be a little bit doubtful that we might be able to kind of basic science our way into understanding things in a very, very useful and very, very rigorous way. In general, I think the deep learning field is has shown to be one that's guided by empirical progress much more than theoretical progress. And I think more specifically, the same has
Hmm.
happened with the interpretability field. One could argue that interpretability for AI safety has been quite popular since maybe 2017, maybe a bit before. And people were saying
Hmm.
very similar things back then, and people are saying very similar things now. And I think these things are these notions that we can make a lot of progress with the basic science are just as valid then as now. But it's notable that we haven't seen, I don't think, any particularly like remarkable forms of progress on this front since then. And I get that that's a very general claim to make. So maybe we can put a pin in that and talk more about some of this later.
So, so with this in mind, with this idea of like kind of the point of interpretability as being like diagnosing and fixing problems, what do you think of like the state of the field of interpretability research?
Yeah, I think it's not actively and reliably, producing tools for this right now. I think there are
Okay.
some, and I think there's some good like proofs of concept and examples of times when you can use interpretability tools very likely competitively to diagnose and potentially debug problems. But this type of work, I think, seems to be the exception a bit more than the rule. And I think that's kind of like okay and to be expected in a certain sense because the field of interpretability is still growing. It's still new. Certainly recently, and maybe even still now, there's a large extent to which it's just pre-paradigmatic, right? We don't fully understand exactly what we're looking for. But I think that it's probably largely the case now and is going to continue to become more and more the case in the future. That in some sense, it's kind of time to have some sort of paradigm shift toward engineering applications or to substantially increase the amount of work inside of the field that's like very focused on this because
Hmm.
I think it's possible. And of course, from an alignment perspective, it's probably needed if we're ever going to be able to like kind of use these tools to actually align something.
Okay. Why do you think it's possible?
So Right now, I think that lots of the progress that's being made from an engineer's perspective related to interpretability is kind of coming from certain sets of tools. It's coming from the ability to use generative models to find and characterize bugs. It also comes from the ability to produce interesting classes of adversarial examples. This is very related. And it also comes from the ability to automate lots of processes, which now generative models and coding models, sometimes things just like chatbots, are able to kind of do in a more automated way. And the tools for these things are substantially better than they were a few years ago, as is the case with most machine learning goals.
Hmm.
And I think now is a point in time in which it's becoming much clearer to much more people that the ability to leverage some of these is like pretty valuable potentially for when it comes to interpretability and other methods for evals.
Okay. Do you have any specific like approaches in mind?
Sure. Take one. Consider this just an example. So a few years ago, we had adversarial patchwork, where people were attacking vision models with small adversarial patches that were just this like localized region of an image. So the adversary was able to control that patch and no other part of the image. So that's the sense in which the adversary's ability to influence the system was limited.
Hmm.
And adversarial patches, kind of back in circa 2017, looked like you would probably expect. They kind of looked like strange things with sorts of structure and pattern to them, but still lots of high frequency patterns, still things that by default were very, very difficult to try to interpret.
Hmm.
A few years later, a handful of works found that you could use generators like GANs to attack the same types of systems with things like adversarial patches, which tended to produce like more and more coherent features. And then a few years after that, like right up close to this state of the art, oh, sorry, to the present day, the state of the art for producing adversarial features is stuff that's all via diffusion models, which are able to produce features that are much more convincingly incorporated into images, and features that are, just kind of look quite a bit better and are much easier to interpret because diffusion models are really good at flexible image editing like this. And I
Hmm.
think this is kind of one example of a progression from like more crude or basic tools to like better tools that can be used for human understandable interpretations. And it was all facilitated just by kind of advances in like the adversaries research and generative modeling. And I
Yeah.
think analogous things are happening in related to other types of interpretability tools too.
Yeah, I'm wondering. So you mentioned there that like the example you gave was in the field of coming up with adversaries to basically, as I understand it, things that can kind of trick image classifiers or other kinds of neural network models. What do you see as the relationship between those and interpretability in general?
Yeah, I think this is one of the takes that I am the most excited about. And I will say quite plainly and confidently that the study of interpretability and the study of adversaries are inextricably connected when it comes to deep learning and AI safety research. And this is one of my favorite topics because I work on both of these things. I usually
Hmm.
describe myself as someone who just works on interpretability and adversaries.
Hmm.
And the space between them, I think, is great. And the space between them, I think, is very neglected. And there's still a lot of low hanging fruit
Hmm.
at the intersection here. And the argument is that there are four particularly important connections between interpretability and adversaries.
Hmm.
One is that more robust networks are more interpretable, and vice versa.
Hmm.
The other is that interpretability tools can help you design adversarial examples, and doing so is a really good thing to do with interpretability tools.
Hmm.
The third is that adversaries are themselves interpretability tools lots of the time, if you
Hmm.
use them right. And the fourth is that mechanistic interpretability and latent adversarial training are the two types of tools that are uniquely equipped to handle things like deceptive alignment.
Yeah, I guess in my head there's this strong connection, which is just like if you want to be an adversary, like if I want to like really mess with you somehow, like the best way I can do that is kind of understand how your brain works and like how you're working so that I can exploit that. And so to me, I don't know, it seems like somehow I mean there's one direction where like coming up with adversarial examples kind of tells you something about the system. But yeah, in the other direction, like it just seems like in order for an adversary to be good enough, it has to quote unquote, understand things about the target network. I'm wondering what you think about that broad perspective.
Yeah, I think that's the right way to think of it. These two things are kind of like very much both sides of the same coin, or
Hmm.
very much like each other's duel. On the notion of using interpretability tools to design adversaries, the case is that you've understood a network very well if you're able to understand it enough to exploit it, right?
Hmm.
And this is an example of doing something that is engineering relevant or of a type that is potentially interesting to an engineer using an interpretability tool. And then on the other hand, where adversaries are interpretability tools, right? If you
Hmm.
construct an adversary, there is a certain sense in which you might argue that like you've already done some sort of interpretation, right? Saying
Yeah.
that this thing or this class of examples or something like that, fools the network. Being able to say that is not unlike an interpretation. It might not be like particularly rich or mechanistic in a sense, but this is something meaningful you might be able to say about a model, right?
Yeah, I mean, it kind of reminds me of so my colleagues now at the Foundation for Alignment Research, it's called FAR. I forget exactly what the letters stand for, but basically they trained this model to beat the best models that play Go. But like the adversaries they trained, they're not like in general very good. Like I don't know, if I taught you Go, like after a day or two, you could beat these adversaries. But to me, like a really cool aspect of their work is that you could look at what the adversary was doing, and like if you're a decent player, you could copy that strategy, which in some sense is like I think is like a pretty good sign that you've like understood something about the victim model basically, and that you understood like how the adversarial attack works.
Yeah, I think I understand things roughly the same way, and I'm really excited about this work for that reason. I'm also
Yep.
very excited about this work because it kind of suggests that even systems that seem quite superhuman still might have some silly vulnerabilities that adversarial examples or interpretability tools might be able to help us discover.
Yeah. So one question this brings me to is like if I think about adversaries and interpretability being super linked, I wonder like what does that suggest in the interpretability space? Like are there any things that are being done with adversaries that like suggests some sort of cool interpretability method that like hasn't yet been conceived of as interpretability?
I think there are some examples of things that maybe are kind of old and well known now, but like aren't usually described in the same settings or talked about among the same people who talk about interpretability tools. For
Hmm.
example, understanding that high frequency, non robust features are things that are still predictive and used by models and are in large part seem to be responsible for adversarial vulnerability. This is a
Hmm.
really important connection to be aware of and to realize because high frequency, non robust, non interpretable features are kind of
Yeah.
the enemy of interpretability.
What do you mean when you say that they're predictive? Like what's true about them?
Yeah, right. My understanding here largely stems from a paper I think from 2019 called
Hmm.
Adversarial Examples or Features, or not bugs, they're features, which kind of studied this in a pretty clever way.
Hmm.
So, your typical LP norm adversarial perturbation is just a very subtle pattern, or a subtle addition or perturbation that you can make to an image or something like this. And
Hmm.
then if you exaggerate it so it's visible, it just kind of looks like this confettified, noisy, perhaps mildly textured set of patterns. But it's not, something that you might predict or that you'd really expect as a human. But when
Hmm.
you apply this to the image, it can reliably cause a model to be fooled.
Yep.
And what was kind of realized by this paper is that like it asks this question: Are these features meaningful? Are they predictive? Are they something that the models are using, or are they just kind of like random junk? And they added to the evidence that these features are useful by conducting some experiments where if you take images and then you give them targeted adversarial perturbations, and then you label those images consistently with the target instead of the source, then to a human, all these images look mislabeled, or
Hmm.
n minus 1 over n of them, that proportion of them look mislabeled. But you can
Yep.
still train a network on this and have it meaningfully generalized to held out, unperturbed data. And that's really
Hmm.
impressive, right? This kind of suggests that networks may be learning and picking up on features that humans are not naturally like disposed to understand very well, but networks can.
Hmm.
And this seems to kind of like be an important thing to keep in mind when we're trying to do interpretability from a human-centric standpoint, right? There might
Hmm.
be trade-offs that are kind of fundamental if you want a human-focused approach to AI interpretability. Humans just might not be able to pick up on everything useful that models are able to pick up on.
Okay. Yeah, so that was example one of a link between adversaries and interpretability. I
Sure.
think you were about to give an example two when I interrupted you.
Yeah, another example is like the Trojan literature, data poisoning attacks that are meant to implant specific weaknesses into models so that they can like have those weaknesses in deployment. This is often
Hmm.
studied from a security standpoint, but it's also very interesting from an interpretability standpoint because the discovery of Trojans is an interpretability problem, and the
Hmm.
removal of Trojans is a robustness problem, right?
Yep.
So there are very, very close relationships between this type of problem and the types of tools that the interpretability literature is is hopefully able to produce. There's another connection too because Trojans are quite a bit like deceptive alignment, where deceptively aligned models are going to have these triggers for bad behavior, but these are by definition or assumption things that you're not going to find during normal training or evals.
Hmm.
So the ability to characterize what models are going to do in a robust way on unseen anomalous data is kind of one way of describing the problem of detecting Trojans, and one way of describing the problem of solving deceptive alignment.
Sure. Yeah, so I actually have some follow up questions about both of the things you said.
Sure.
Yeah, we're sort of like skirting around things that you mentioned in this like sequence, the engineer's interpretability sequence. And yeah, one claim I think you make is that with regards to the first thing you mentioned, the existence of these like useful features that aren't like robust and seem like adversarial noise, that this kind of weighs against the use of human intuition in interpretability. And I'm wondering like how strongly it weighs against this. So like one analogy I could imagine making is like sometimes in math there'll be some pattern that appears like kind of random to you, or like you don't like really understand why it's happening. And then like there's some, theorem with like an understandable proof that explains the pattern. Like you wouldn't have understand the pattern like without this theorem, but like there's some mathematical argument that like once you see it, things totally make sense. And you could imagine like something similar in the case of these like non-robust features, right? Where like the network has some like really unintuitive to humans behavior, but like there's a way of explaining this behavior that uses intuitive facts that eventually makes this intuitive to humans. So I don't know. I'm wondering like what your reaction is to that kind of proposal.
Yeah, I think this makes sense, right? Because earlier when I say like a human-centric approach to interpretability, the kind of thing that's in my head is just the idea of humans being able to look at and study something and easily describe in like words what they're looking at or seeing or studying. And this is not the case with adversarial perturbation or typical adversarial perturbations, at least in images.
Hmm.
But you bring up this notion like, is it possible that we could relax that a little bit and use something else? And I think this makes sense. You'd probably just have to have some sort of change in the primitives with which you describe what's going on. Right? You can probably describe things in terms of specific, adversarial examples or perturbations or modes or something like
Hmm.
this. Even if, like, by themselves, if you looked at them, it just kind of looks like glitter in an image and looks like nothing that you could easily describe.
Hmm.
And I think this is like very, very potentially useful, right? This is kind of not the type of thing I meant when I talked about a human-centric approach to interpretability, but it
Hmm.
sounds like unless we want to have, trade-offs with, models' performance or something like this, it would do us well to like go in and try to understand models more flexibly than in terms of just what a human can describe. But
Hmm.
if we are to do this, it's probably going to involve a lot of automation, I assume.
Yeah. Yeah. How do you see the prospects of using automation in interpretability research?
I think it's probably going to be very, very important and central to like highly relevant forms of interpretability.
Hmm.
And it's possible that this claim could age poorly, but I do think it'll age well, and people can hold me accountable to this at any point in the future.
Okay.
So lots of interpretability, lots of very rigorous specifically rigorous mechanistic interpretability research has been done at relatively small scales with humans in the loop, right?
Hmm.
And we've learned some pretty interesting things about neural networks in the process, it seems. But there's a gap between this and like what we would really need to, fix AI and save anyone in the real world, right? Studying things in very small transformers or very limited circuits and CNNs, these types of things, are pretty small in scale and toy in scope. So if we are to take this approach of kind of rigorously understanding networks from the bottom up, I think we're probably going to need to apply a lot of automation tools. And there are a few like
Hmm.
topics here that to talk about. One is like what's already been done. There's some topics involving how this kind of fits into agendas related to mechanistic interpretability and causal scrubbing, which is a whole other thing we can get into. This
Yeah.
this definitely has a few rabbit holes we can get into.
Yeah. I mean, I guess, first of all, let's talk about mechanistic interpretability a little bit. First of all, what do you understand the term to mean for those who haven't heard it?
Yeah, that's a pretty good question. Mechanistic interpretability, also like circuits, are and interpretability itself. Some of these things are just like vocab terms that people usually use to mean whatever they want. And I don't say that in a pejorative way. Like I do this too. I use these things to refer to anything I want them to mean. But
Okay.
I guess this lends itself to a general definition of mechanistic interpretability. And I think I'd probably just describe mechanistic interpretability as anything that helps you explain model internals or details about algorithms that the model internals are implementing, something like this. But the emphasis is that like you're opening up the black box and you're trying to characterize the computations going on and passes through a network.
Okay. And yeah, you mentioned that you think like at some point this will need to kind of be automated or scaled up. Is that because you think like it's a particularly important kind of interpretability that we need to do, or yeah, what do you think about the role of it?
Yeah, if you pose the question that way, then I think that there are two very important points that I feel strongly about, but I feel
Hmm.
very strongly about them in ways that have a completely different ethos, right? On one hand, mechanistic interpretability is one of these tools, one of these methods or paradigms that can
Hmm.
help us rigorously, if it works, can help us hopefully rigorously understand networks well enough to find and empower us to fix particularly insidious forms of misalignment, like deceptive
Hmm.
alignment, or like a paperclip maximizer who is trying to actively deceive you into thinking it's aligned even though it's not. There
Hmm.
aren't that many tools at the end of the day that are going to be very useful for this, and mechanistic interpretability is one of those tools. So
Hmm.
there's one sense in which I think we really, really need it. There's another sense in which I think it's just very, really, really hard. And there's a big gap between where we are now and where we would want to be from an engineer's perspective.
Hmm.
The reason it's really, really hard is because mechanistic interpretability is really a problem with two different parts. You start with a system. Part one is coming up with mechanistic hypotheses to explain what this system is doing. So this could be in terms of like pseudocode. A mechanistic hypothesis could look like some sort of graph. And a hypothesis doesn't have to be like one function or program. It could represent a class of functions or programs. But it needs to
Hmm.
be some sort of representation of what's happening mechanistically inside of the network. Step two is to then take that hypothesis, that mechanistic hypothesis, and test to what extent it validly explains the computations being performed internally inside of the network. So, right, step
Hmm.
one, hypothesis generation. Step two, hypothesis confirmation. I think step two is tractable, or at least it's the kind of thing that we're able to be making progress on. For example, the causal scrubbing agenda is something that's pretty popular in relating to this. That's had a lot of work done recently. It's a relatively tractable problem to try to come up with methods to confirm like how computationally similar a hypothesis graph is to what a system is doing.
Hmm.
Step one, though, seems quite difficult. And it seems about as difficult as program synthesis slash program induction slash programming language translation. And these are things that are known to be quite hard and have been known to be quite hard for a long time. And lots of progress has been made in mechanistic interpretability by focusing on very simple problems where the hypotheses are easy. But in general, if we don't assume that we're going to encounter a bunch of systems in the future where the things that are right or wrong about them are explainable in terms of easy hypotheses. I don't think that we're going to be able to get too much further or scale too much higher by kind of relying on toy problem, human in the loop approaches to mechanistic interpretability.
Yeah, I guess I have a few thoughts in response to that. So the first is like when you say that like coming up with hypotheses seems about as hard as like program synthesis or like program translation. It's not clear to me why this. I mean, I guess I can see how it's closer to program translation.
Hmm.
I mean, unlike synthesis, you have access to this neural network which is doing the thing. Like you have access to all the weights. In some sense, you know exactly how it works. And it seems to me that there is some ability, like we have tools that can tell you things about your code. For instance, like type checkers. Like that's a tool that is, I guess, like quasi mechanistic. It really does like tell you something about your code, right? I don't know. I was wondering if you could elaborate more on your thoughts about like how difficult you expect hypothesis generation to actually be.
Yeah, I think that's a good take. And it's probably worth being a slightly more specific at this point in time. So, if you're forming mechanistic hypotheses from the task or the problem specification,
Hmm.
then that's much like program synthesis.
Yep.
If you're forming these from input output examples from the network, this is much like program induction. And then, like you said, if you're forming them through model internals, this is much like programming language translation because you're trying to translate between different formalisms for computing things, right?
And in this case, you have all three sources of information, right?
Yeah, and in this case, you do, which is nice. I don't know of this like being some sort of like theoretical solution around any like proofs of hardness for any of these problems, but in
Hmm.
practice, it is nice. This is certainly a good thing to point out, and it's probably going to be useful. But then there's this notion of like like how can we make some sort of progress, right?
Hmm.
From this like translation perspective. And if we wanted to do it particularly rigorously, if we were like, if we shot for the moon, we might land on the ground because it might be very hard to like just turn a network into a piece of code that like very, very well describes it. But you mentioned the analogy to like type checkers, right? Type checkers are kind
Hmm.
of nice because you can run them on things and being able to determine something's type or being able to determine if there's like a likely syntax error or something is not something that is like made impossible by like Rice's theorem or uncomputability results.
Hmm.
And to the extent that we're able to do this inside, do something analogous, or like find flags for interesting behavior, or things to check out, or parts of the architecture to scrutinize more, or things that we might be able to like cut out, or things that might be involved in handling of anomalous inputs, anything like this. I think these sound very cool.
Hmm.
And I think what you just described would probably be one of the best ways to try to move forward on a problem like this. It's not something that I'll say I have a lot of faith in or not, just because I don't think we have a lot of examples of this type of thing. But
Hmm.
I would certainly be interested to like hear more work about doing something like this, about kind of learning useful heuristics or rules associated with like specific networks or something that are flag interesting things about it. And
Yeah.
I like this idea a lot.
And I guess like yeah, when you mention like is your the thing you're trying to do barred by Rice's theorem? So
Mhm.
Rice's theorem says that like you can correct me if I'm wrong, but I think it says that for any property of a program such that the property isn't about how you like wrote the program, it's about like its external behavior.
Mhm.
And there are some programs that it's like a non-trivial property, like some programs have this property and some programs don't have the property, then like you can't always determine by running code whether any given program has this property. Like in theory, there are examples that you just like can't work with,
Yes.
and I think that suggests that like in some sense we should probably like try to have neural networks that aren't just generic computer programs, like where we do know that these kinds of things will work. And similarly, the analogy to program translation, like, I don't know, it's probably better if you write your code nicely. Similarly, I don't know, I'm aware that there's
Hmm.
So in a podcast that I recorded but not yet released with Scott Aronson, he mentions this result where like in the worst case, it's possible to like take a two-layer neural network, implant a basically a Trojan, a backdoor in it, such that the task of finding out that that happened is equivalent to like some computationally difficult graph theory problem, right?
I assume this involves a black box assumption about the network, right? Not that you have access to model internals.
No, even white box. You have access to the weights,
Oh,
but
you do?
like
Okay.
yeah, if you think about it, having access to the weights is sort of like having access to some graph, and like there are some computationally difficult problems with graphs, right? So yeah, I guess if I put this all together, then I might have some vision of like, okay, we need to like structure, we need to somehow ensure that models have a nice kind of structure so that we can mechanistically interpret them. And then I start thinking, okay, well, maybe the reason you start with toy problems is that you get used to trying to figure out like what kinds of structure actually helps you understand things and like explain various mechanisms. I don't know. That was mostly my take. So, what do you think about all that?
Sure. So, this idea that profess to be a fan of, this idea of um, doing something analogous to like type checking. I think, and you bring up this idea of like making networks that are like good for this in the first place or very amenable to this in the first place.
Hmm.
Um, I think that a post hoc version of this, or a version of this where you're just like looking at model weights in order to like flag interesting parts of the architecture. I think I don't know of any examples on the top of my head that are like particularly good examples of this. There's stuff like mechanistic anomaly detection that could maybe be used for it, but I don't know of a lot of work that's immediately being done, at least from this post hoc perspective. Does anything come to mind for you? There probably is something out there, but my point is something like I don't know of a lot of examples of this, but maybe it could be kind of cool to think about in the future.
To be honest, I know a little bit less about the
All right.
interpretability literature than maybe I should.
But then there's this non-post hoc notion of doing this,
Pre-hoc,
really
one
the
might say.
pre-hoc, where or intrinsic way in which you want an architecture that's like that has nice properties related to like things you can verify about it or like
Hmm.
modularity or something. And I think this work is very, very exciting. And I think obviously there's a lot of work on this from the literature at large. There are all sorts of things that are directly getting at simpler or more architectures or architectures that are easy to study or more interpretable or something of the sort. But one thing I think is a bit interesting about the AI safety interpretability community is that there's a lot of emphasis on analyzing circuits. There's a lot
Hmm.
of emphasis on this type of problem, mechanistic anomaly detection.
Hmm.
And there is a bit less emphasis than I would normally expect on intrinsic approaches to making networks more trainable. Sorry,
Hmm.
more interpretable. And I think this is possibly like a shame or an opportunity that's being missed out on because there are a lot of nice properties that like intrinsic interpretability techniques that can add to neural nets, and there are lots of different techniques that don't conflict with using each other. And I think it might be very interesting, sometime in the near future to just kind of work on more intrinsically interpretable architectures as like a stepping stone to try to do better mechanistic interpretability in the future. Like,
Hmm.
for example, how awesomely interpretable might some sort of neural network that is adversarially trained and trained with elastic weight consolidation and trained with bottlenecking or some other method to like reduce polysemanticity. And maybe its architecture is sparse and maybe there's some intrinsic modularity kind of baked into the architecture. Something like this, right?
Hmm.
How much easier might it be to interpret a neural network that is kind of optimized to be interpretable as opposed to just kind of like trained on some sort of task using performance measures to evaluate it and then something that you just use interpretability tools on after the fact.
Hmm.
I think it's a shame that we have like all this pressure for benchmarking and developing AI systems to be like good at performance on some type of task, while not also having like comparable feedback and benchmarking and pressures in the research space for properties related to interpretability.
Yeah. I mean, I think one reaction that people often have to this instinct is to say, look, like the reason that deep neural networks are so performant, the reason that they can do so much stuff is kind of because they're these like big sort of semi-unstructured blobs of matrices, right? Such that gradients can like flow freely and the network can kind of like figure out its own structure. And I think there's some worry that like, in most ways you're going to think of like imposing some architecture are like going to run contrary to like Rich Sutton's bitter lesson, which is that like, no, you just need to like have methods that like use computation to figure out what they should be doing and just only do things which scale nicely with computation.
Yeah.
So yeah, how possible do you think it's going to be to reconcile like performance with architectures that actually like help interpretability in a real way?
Yeah, I expect this to be the case definitely somewhat. Most of the time, when some type of interpretability tool is applied, or a type of intrinsic interpretability tool is applied, task performance goes down. Like if you adversarially train an ImageNet network, it's not gonna do quite as well as a non-adversarially trained network on clean data. And obviously, we also know it's quite easy, it's quite trivial to like regularize a network to death. That's about as simple as like setting some sort of hyperparameter too high.
Hmm.
So there's kind of this question about like, is there good space to work in the middle between maximally performant networks and over-regularize impotent networks? And when framed that way, I think you see the answer I'm getting at. It's probably something like we just got to find the sweet spot and
Hmm.
see how much of one we're willing to trade off for the other. But we're probably also going to find a lot of things that are just better than other things. Maybe like pruning. That's an intrinsic interpretability tool. If you have a network that is more sparse and has fewer weights, then you have less to scrutinize when you want to go and interpret it later, so it's easier. Maybe this just isn't as effective as an interpretability tool for the same cost and performance as something else. Maybe adversarial training is better for this one for lots of classes of interpretability tools. And even if there is some sort of fundamental trade-off, just maybe it's not too big, and maybe there are ways to minimize it by picking the right tools or combinations thereof. But I continue to be a little bit surprised at just like how relatively little work there is on combining techniques and looking for synergies between them for results-oriented goals involving interpretability or for engineering goals involving interpretability. So
Hmm.
it could be the case that this isn't like that useful for having competitive performant networks, but I certainly still think it's worth trying some more. Well, almost trying, period, but
Hmm.
working on in earnest.
So so you brought this up as kind of a complaint you had about the kind of AI safety interpretability community, which I take to mean this sort of community around like, I don't know, Anthropic, Redwood Research, people who are worried about AI causing existential
Sure.
risk. And you mentioned this as like a thing that they could be doing better. I think maybe many of my listeners are from this community. Yeah. Do you have other things that you think they could improve on?
Yeah. So, and I talked about a few of these. I enumerated a few of these in the engineer's interpretability sequence.
Hmm.
And in one sense, the AI safety interpretability community is young and it is small. So obviously, it's not going to be able to like do everything. And I think it's probably about equally obvious that so much of what it is doing is very, very cool, right? We're having this conversation, and so many other people have so many other conversations about many interesting topics just because this community exists, right? So I want to be clear that I think it's great. But I think the AI safety interpretability community also has a few blind spots. Maybe that's just inevitable given its size. But the point we talked about involving like mechanistic interpretability having two parts, and there's the first part being hard, is one of
Hmm.
these. The relative lack of focus on intrinsic interpretability tools, like I mentioned, is another. And I also think that the AI safety interpretability community is sometimes a little bit too eager to like just start things up and sometimes rename them and sometimes rehash work on them, even though there are close connections to more mainstream AI literature. I know of a couple examples of this, but a strong one involves like the study of disentanglement and polysemanticity in neural networks. This is something that I talked about a bit. I don't want to like overemphasize this point in the podcast, but we could talk a bit about one case study involving kind of like a possible insularity and possible isolation of research topics inside of the AI
Sure.
safety interpretability community.
Yeah, sure.
So we have this notion that's pretty popular inside the interpretability community here of like polysemanticity and superposition. And these are kind of things that are bad or like the enemies of useful, rigorous interpretability. And it's pretty simple. The idea is that if a neuron responds to multiple distinct types of like semantically different features, then it's polysemantic, right? If there's a neuron that fires for cats and for cars, we might call it polysemantic.
Mm.
And superposition is a little bit more of a general term that applies to like a whole layer or something like this. If neuron is exhibiting superposition in as much as it is polysemantic, and a layer is exhibiting superposition in as much as it represents concepts as linear combinations of neurons that are not all orthogonal, right?
Mm.
There's crosstalk between the activation vectors that correspond to distinct concepts.
Mm.
And these are useful terms, but these terms are also very, very similar to things that have been studied before. The polysemanticity and superposition crowd has pointed out this similarity with sparse coding, but much more recently, there's been a lot of work in the mainstream AI literature on disentanglement. And this
Yep.
goes back significantly before the literature on polysemanticity and superposition. And its disentanglement just describes something very similar. It's when there's superposition, or when for some reason or other you don't just have a bijective mapping between neurons and concepts.
Mm.
And it's not that renaming something is intrinsically bad, but I think for community reasons, and there has been a bit of isolation between the AI safety interpretability community on this topic and then other research communities, that's been facilitated by having different vocabulary. And at best, this kind of is a little bit confusing, and at worst, this could maybe lead to isolation among different researchers working on the same thing under different names. And there's a case to be made that this is good. Sometimes studying things using different formalisms and different vocabularies can contribute to the overall richness of what is found. For example, studying Turing machines and studying lambda calculus. These both got us to the same place, but arguably we've had some richer insights as a result of studying both instead of just studying one. And this could be the case. But I think it's important to emphasize maybe putting some more effort into avoiding rehashing and renaming work.
I mean, so in the case of polysemanticity and disentanglement, I mean, I think it's worth saying that, I think one of the original papers on this topic talks about the relationship to disentanglement. But, do you think that, do you see there as being insights in the disentanglement literature that are just, that are being missed? Or, I don't know, can you go into more detail about, what problems you think this is causing?
Yeah, and it should be clear that there is citation. There are those pointers that exist, although arguably not discussed in the optimal way. But that's less important. Here's an example. So if we think about what the distill and anthropic communities, which are pretty prominent in the AI safety interpretability space, the types of work that they've done to solve this problem of superposition or entanglement.
Hmm.
Most of the work that's been done is to study it and characterize it, and that's great. But there's
Hmm.
roughly one example of which I am very familiar with for explicitly combating polysemanticity and superposition and entanglement. And
Hmm.
that is from the paper called softmax linear units, right, which describes an activation function that is useful for reducing the amount of entanglement inside of these layers. And that
Hmm.
activation function operates, the reason it works is because this is an example of an activation function that causes neurons to compete to be able to be activated. It's just a mechanism for lateral inhibition. But lateral inhibition has been understood to be useful for reducing entanglement for a while now. There
Hmm.
have been other works on lateral inhibition and different activation functions from the disentanglement literature. And there's also been quite a few non-lateral inhibition ways of tackling the same problem as well from the disentanglement literature. And I
Hmm.
think that the softmax linear units work was very cool and very interesting. And I'm a smarter person because I've read it. But I'm also a much smarter. I'm also a smarter person because I have looked at some of these other works on similar goals, and I think things are kind of a bit richer and a bit more well fleshed out on the other side of the the divide between the AI safety interpretability community and the more mainstream ML community. So yeah, the softmax linear unit paper was cool. But as
Hmm.
we continue with work like this, I think it'll be really useful to take advantage of the wealth of understanding that we have from a lot of work in the 2010s on disentanglement, instead of just kind of trying a few things ourselves, reinventing the wheel in some sense.
I guess, could you be more explicit about the problem you see here? Because, I mean, in the paper about softmax linear units, they do say, here are some things which could help with polysemanticity, and like one of the things they mention is like lateral inhibition. I don't know if they talk about its presence in the disentanglement literature, but like given that they're using the same language for it, I'm not getting the impression that they had to like reinvent the same idea. So,
Yeah, I think the claim is definitely not that like the authors of this paper were unaware of anything like this.
hmm,
I think the authors of this paper probably like are, but the AI safety interpretability community as a whole, I
hmm,
think, is kind of like a little bit different, and as there's the result of like kind of what bounces in between, this kind of in between this community is kind of a social cluster. There's a bit of a difference between like that and like what's bouncing around elsewhere. And as a result, I think something like softmax linear units might be like overemphasized or thought of more in isolation as a technique for avoiding entanglement or superposition,
okay,
while a good handful of other techniques are kind of like not emphasized enough. Maybe the key point here is just something that's like very, very simple. And it's just that, just based on some kind of claim that it's like important to make sure that all relevant sources of insight are like tapped into if possible, and the extent to which the AI safety community is like guilty of being isolationist in different ways is probably like debatable, probably like not a very productive debate either. But regardless of that exact extent, I think it's probably pretty useful to emphasize that like lots of other similar things are going on in other places.
okay. And so it sounds like, just to check that I understand, it sounds like your concern is that people are reading like, I don't know, anthropic papers or papers coming out of certain labs that are sort of quote unquote in the this AI safety interpretability community, but there's other work that's just as relevant that like might not be getting as much attention. Is that roughly what you think?
Yeah, I think so. And I think this is like an effect, and I'm also like a victim of this effect, right? There's so much like literature out there in
Yeah,
machine learning, you can't read it all, and if you focus on the AI safety part of the literature a bit more, you're going to be exposed to what people in the AI safety community, interpretability community, are talking about. And so this is kind of inevitable. It's kind of something that'll happen to some extent by default, probably, and it happens to me with the like information that I look at on a day-to-day basis. So maybe there's some kind of like point to be made about how it's possible. It's likely. I would say it's probably pretty likely that it would be good to work to resist this a bit.
sure. I'm wondering if like there are any like specific examples of work that you think are maybe under celebrated or little known in the AI safety interpretability community,
So work from outside the community that's like under celebrated and inside of the AI safety interpretability community.
or even inside, but probably work outside that, I don't know, things that like you think should be better known than they are inside this AI safety interpretability community.
Yeah, I think that's a really good question. I probably don't have a commensurately good answer, and maybe my best version of the answer would end up would involve me like listing things involving adversaries or something like this.
Okay,
But I definitely am a fan of like, let's say, one type of research. I'll like, so yeah, there are lots of answers to this, and you can probably find versions of it in the ASA in the engineer's interpretability sequence. But I'll laser in on one that I think I'm pretty excited about, and that is on like the automated synthesis of interesting classes of inputs in order to study the solutions learned by neural networks, particularly problems with them. And
hmm.
this should sound familiar because I think this is the stuff we've already talked about. Examples of this include like synthesizing interesting adversarial features, or examples of this include controllable generation. Examples of this include seeing what happens when you perturb model internals in particularly interesting ways in order to like control the end behavior or the type of solution a network is learned. And I
Hmm.
think there are examples of all of these things from the AI safety interpretability community because they're relatively broad categories. But I think some of my
Yep.
favorite papers in lots of these spaces are from outside of the AI safety interpretability community, from like different labs who really like adversaries.
Hmm.
Yeah, I think my answer here is not the best, but
Okay. I mean, on that front, are there any labs in particular that you'd want to shout out as like?
for example, I think that the Madri lab at MIT does really, really cool interpretability work, even though
Hmm.
they probably don't think of themselves as like interpretability researchers, and the AI safety interpretability community might not necessarily think of them as interpretability researchers either. At one point in time, I constructed a list based on my knowledge of the field of papers from the adversaries and interpretability literature that seem to demonstrate some sort of very engineering relevant and competitive capabilities for model diagnostics or debugging.
Hmm.
Doing stuff that engineers ought to be very interested in, using tools that are interpretability tools or similar. And this list is, I want to be clear, inevitably is like subjective and arbitrary and incomplete. But this list had like 20, I think like 21 or 22 papers on it.
Hmm.
And for what it's worth, the majority of them, these papers, did not come from people who are like prototypical members, or like people who are a typical like member of the AI safety community, interpretability community. Some did, and for those that didn't, many of them are adjacent to the space. But just think there's a lot of cool stuff going on in a lot of places, I guess.
Okay, cool.
Oh, by the way, this list is in the second to last post in the engineer's interpretability sequence, and it's already
Okay,
outdated. I should say.
sure. Yeah, ML is proceeding at a quick pace. So, one thing you also touch on, I guess you said it a little bit earlier, and you've touched on it in the piece, is the relationship between mechanistic interpretability and deceptive alignment. I'm wondering, like, what do you think, like, the relationship between those things is?
Yeah, I think it's kind of like the relationship between interpretability and adversaries. I would describe the relationship between mechanistic interpretability and deceptive alignment as being one of like inextricable connection.
Okay.
Kind of understanding this probably requires me to clarify what I mean by deceptive alignment, because deceptive alignment has been kind of introduced and defined in terms of like colloquially, imagine some sort of like super intelligent system that like wants to hide its misalignment from you, so it actively tricks you into this in some way, shape, or form.
Hmm.
And it's been described and characterized originally in like early posts on the topic about something that is done actively by a system that has a model of itself and of you. And this is something that, as alignment researchers, we're all very worried about. But I think there's a more like general or more like distilled understanding of deception that can come with fewer details attached to it. And that is that if the system is deceptively aligned, whether its problems are being hidden from us actively or not, I think seems less important to an engineer. Just it's that if a system is deceptively misaligned, it has problems, and those problems are going to be ones that are really, really hard to find during testing and evaluation. The types of things we'd normally easily be able to throw at models to figure out if they're aligned with our goals or not.
Hmm.
So basically, it just means that the system has problems that are triggered by anomalous inputs. I would claim that this is something that is very general in a way that captures most of what we care about when it comes to deception. Let's understand deception, for at least the purpose of this conversation or the next few minutes, as being an issue where a model is misaligned, but it's hard to find the things that elicit the misaligned behavior.
Hmm.
So, why is mechanistic interpretability really key to deception in this sense? So, there's a really good example that illustrates a few points from, I think, Paul Christiano originally introduced this, but there's like a deceptively aligned system that is really, really, really insidiously deceptive. So imagine, let's go back to thinking about superintelligences. You have a superintelligent system that's misaligned and has goals that are not your goals, but it understands your goals and it wants you to think that it has your goals. And it wants to take over the world or maybe destroy the world. But it can't try to do that in like training or in simulation or in evaluation, because then you'll stop it. You'll press the off switch or you'll update it, you'll fix something about it. But it wants to self-preserve. So its strategy is to like pick some sort of trigger to trigger its deceptive, misaligned, treacherous behavior, but something that's not going to show up in training or evaluation,
Hmm.
but instead something that's going to show up eventually in deployment.
Hmm.
And the example that Paul Christiano gave was picking some sort of cryptographic puzzle and waiting till it gets solved, and then acting treacherously once it has been solved, because cryptographic puzzles take a long time to solve. And
Hmm.
if you wait till one has been solved, you're likely very far in the future and presumably in deployment.
Hmm.
So The example Paul gave was waiting till the composite number RSA 2048 has been factored. And this is hard,
Yep.
like cryptographically hard. So the reason why this is a great example is because it illustrates a situation in which a system might actively want to be deceptive and might be deceptive in a way that is very, very, very insidious. This deception is cryptographically hard to find.
Hmm.
And provably cryptographically hard to find. It's kind of trivial. Imagine you just like have some language model and it will only ever output the words "I will destroy the world." Once it sees the factors of RSA 2048 inside of its input. So maybe there's only
Hmm.
like one input that could ever cause this problem.
Hmm.
So this is very, very challenging, and it kind of illustrates the hard, at least in theory, part about this, about like using evals and any other types of tools to figure out problems in models. The proof that this is hard makes a black box assumption about the model.
Hmm.
But if you assume you can open up the black box and characterize the system mechanistically, then you have a much better foothold or a much better chance of characterizing the deception in a tractable way or finding the bug in a tractable way.
Hmm.
So this is why mechanistic interpretability, this is where it comes in as being something that's so useful, at least in theory, or sort of promising for alignment. It's a type of tool that could help us like figure out this problem mechanistically as opposed to from inputs and outputs. This is one of the reasons why it plays such a central role in any type of very rigorous agenda for building aligned, safe AI, because it deals with those model internals. And it's one of two approaches, I think only two approaches that are potentially useful for combating this type of deceptive failure.
Well, now I want to know what do you think the other approach is?
The other would be mechanistic adversarial training or latent adversarial training.
Hmm. Yeah, what's that?
So really concretely imagine the system that's going to destroy the world once it sees the factors of RSA 2048. Imagine concretely that there's just a single neuron or something inside of it
Hmm.
that detects whether this number has been factored and or whether the factors have been shown, and then triggers this some sort of circuit inside the model in order to enact the treacherous behavior. And this is too
Hmm.
simple, and more generally, it could be some sort of like set of neurons or direction or circuit or anything like this. But I don't know, just think about it as being a neuron for simplicity. Just like mechanistic interpretability can help you find this neuron, latent
Hmm.
adversarial training could give you perturbations to the model internals, such as this neuron,
Hmm.
that are going to help to elicit potentially bad behavior during training so that you can make the model more robust, not just to attempted adversarial inputs that you find, but also synthetic adversarial inner hallucinations, right?
Yep.
It just might be a lot easier to make models hallucinate that they want to do something bad or just hallucinate triggers for bad behavior than to make them actually find those triggers for bad behavior in the input space.
Yeah, and just to spell that out, I guess the idea is you like find these inputs which make it do something bad during training, and then you just train it to not do that. Like hopefully you train it such that there's no hallucination of some benign event where it like goes evil. Is my understanding.
Yeah, and did you say inputs? But like, it can be the activations of any internal part of the
Yeah, yeah.
network, right? Yeah.
One kind of question I have about this approach is it seems like it's very closely related to mechanistic interpretability. The reason being, like, suppose, well, like for basically any output that your AI could have, there are cases where that output is desired, right? Like, otherwise, you could just like set up a filter at the end of your AI, being like, just make it impossible to have
Hmm.
this output, right? And so, like, you could imagine like there's for some undesired output, maybe there's an early on neuron that says like, yeah, it checks if there's some factorization of this really large number, and then it does this naughty thing.
Hmm.
Or like maybe late, somewhere else in the network, there's this neuron that checks if there's like an actually really good reason to do this thing, which like at first seems naughty. And then like if there is a really good reason, then it does it, right? And kind of by construction, if you've done things sensibly, like for every output of your neural network, there must be like some trigger that would make it a good idea. So it seems like in order to distinguish between like hallucinations where it's justified to do this thing versus hallucinations where it's unjustified to do this thing, it seems like you need to have some mechanistic understanding of like what's going on inside the model. I'm wondering what you make of that claim.
Yeah, this is a good point. And I think there are a few things I have in mind. One
Hmm.
is that if you think of like a classifier, or like some sort of discrete action space, if a network can only do like a discrete set of things, then obviously you're only going to design it to do the set of discrete things that you would ever want it to do, right?
Hmm.
You're never going to design like a discrete action space for some sort of agent where one of the actions is destroy the world and everything else is benign, right?
Yeah.
But for something where the outputs are non-discrete, like a language model, or the ability to detect whether something is bad is like not trivial. It's not like if a single word has been said, then your system will usually be able to do things that are wrong that you're not trivially able to detect. So for example, maybe you take a language model and you train it to never ever ever say an offensive word, and that's easy to like supervise. And you could like even design out the tokenizations of your list of offensive words and not even include them in the model's ability to
Hmm.
process anything. But the model still might be able to like lie.
Hmm.
You won't be able to prevent it from lying using some type of approach like this. But then there's the second point. Like you bring up this idea that like, well, if we can detect this, right? If we can detect whether something, to the extent that we're able to detect whether something's a lie, then we can do something like latent adversarial training. But if we can detect whether something's a lie or something's bad, then like, what's the need for this, right?
Hmm.
So yeah, why not just use a classifier as a filter or something? And this is kind of pointing out that if like we're really, really, really good at solving outer alignment, or figuring out how to specify our goals or
Hmm.
recognize failure for a system, maybe this is a partial solution to just the inner alignment problem, which is all about getting systems to correctly optimize for what we tell them to optimize for. And I think this is very true. To the extent that we're able to recognize failure, in theory, we can just always filter outputs that are bad. In practice, though, I think we're going to run into challenges largely involving efficiency, right? Maybe, as is kind of assumed with something like reinforcement learning from human feedback, maybe our ability to recognize bad behavior is, just like by a human looking at something and telling whether or not it's okay or whether it's bad. That's not something that we can like very efficiently tack onto a system, even in training, let alone deployment all the time. Right. So we have to take these shortcuts. And I certainly would want it to be an additional tool in the toolbox, in addition to filters, to have the ability to train models that are more intrinsically and endogenously robust to the problems that we can recognize. A good thing about these types of different approaches is that certainly they don't seem mutually exclusive.
Hmm. So, one thing, I guess, very related to this problem of deceptive alignment is detecting Trojans. Can you talk a little bit about how you see those as being similar?
Yeah. So a little bit earlier, I kind of made the case for one broad way of understanding deception as just being when a system develops, for whatever reason, bad behavior that will be a response to some sort of anomalous input, some sort of anomalous inputs that are like hard to find or simulate during training and evaluation.
Hmm.
And this is quite close to the definition of what a Trojan is. So a Trojan or a backdoor kind of come from the security literature. This wasn't first; these aren't concepts that are first from machine learning, but they've kind of come to apply in machine learning, and roughly synonymously, just both Trojan and backdoor refer to some sort of particular subtle weakness or sneaky weakness that has been engineered into some sort of system. So just
Hmm.
a Trojan is like some misassociation between like a rare feature or a rare type of input and some sort of unexpected, possibly bad or malicious behavior that some sort of adversary could implant into the network. The way
Hmm.
this is usually like discussed is from a security standpoint. It's just like, oh, imagine that someone has access to your training data. What types of weird weaknesses or behaviors could they implant in the network? And this is really useful, actually. Like think about just the internet, which has now become the training data for lots of state-of-the-art models. People could just put stuff up on the internet in order to like control, well, sorry, what systems trained on internet scale data, might actually end up doing.
Hmm.
But the reason this is interesting to the study of interpretability and adversaries and AI safety is less from this security perspective and more from the perspective of like how tools to characterize and find and scrub away Trojans are very related to the interpretability tools and research that we have. And they're very much like the task of finding triggers for deceptive behavior. There are very few differences, and the differences are practical, not technical mostly, between deceptive failures and the types of failures that Trojans and backdoors elicit.
Sure. So I think this is a good segue to talk about your paper called Benchmarking Interpretability Tools for Deep Neural Networks, which you co-authored with Yuxiao Li, Jiawei Li, Tongbu, Kevin Zhang, and Dylan Hadfield-Manel. I hope I didn't get those names too wrong.
No, sounds right.
But it's basically about benchmarking interpretability tools for whether they can, detect certain Trojans that you implant in networks, right?
Yes. And one quick note for people listening to this in the future. The paper is very likely to undergo a renaming, and it is likely to be titled Benchmarking AI Interpretability Tools Using Trojan Discovery as well. So similar title, but likely to change.
All right, cool. Well, I guess you've made the case for it being related to deceptive alignment, but I think I'm still curious why you chose Trojans as a benchmark. Like, I don't know if I was like kind of thinking of I kind of brainstormed like, well, if I wanted to benchmark interpretability tools, what would I do? And like, I guess other possibilities are like predicting downstream capabilities. For instance, like if you have a large language model, can you predict like whether it's going to be able to solve math tasks, or like can you like fine tune your image model to do some other task? You could also do like just predicting generalization loss, like what loss it achieves on data sets it hasn't seen. You could try and like manually distill it to a smaller network. I don't know. There are a few things you could try and do with networks, or a few facts about networks that you could try to have interpretability tools find out. So I'm wondering like why Trojans in particular.
Yeah, the types of things you mentioned, I think I find them pretty interesting too. And I think that
Okay.
any type of approach to interpretability, especially mechanistic interpretability, that like goes and finds good answers to one of these problems seems like a pretty cool one.
Hmm.
But yeah, we studied Trojans in particular. And in one sense, I'll point out there is a bit of a similarity between discovering Trojans and some of the things that you described. For
Hmm.
example, if you're asking like what's the Trojan versus if you're asking how is this model going to perform when I give it math questions, or if you're asking how is the model going to behave on this type of problem or that type of problem,
Hmm.
there's something a bit similar in all of these types of tasks. And that's a sort of sense in which you're trying to like answer questions about how the model is going to be behaving on interesting data, specifically if that data is unseen. That's another nice thing about a benchmark, hopefully, because if you already have the data, then why not just run it through the network?
Hmm.
But Trojans, right? So like, why do we use Trojans? One reason is that there's a very well-known ground truth. The ground truth is kind of easy to evaluate. If you are able to successfully match whatever evidence an interpretability tool produces with the actual trigger corresponding to the Trojan, then you can say with an amount of confidence that you've done something correctly.
Hmm.
Other interpretability tools could be used for characterizing all sorts of properties of networks, and not all of them are like Trojans in the sense that there's some type of like knowable ground truth.
Hmm.
And some of them are, but not all of them. Another advantage of using Trojans is that they are like very easy. They're just kind of very convenient to work with. You can make a Trojan trigger anything you want. You can insert it any type of way you want to, using any type of like data poisoning method. And the point here is also making them something that's like a very novel, very distinct feature so that you can again like evaluate it later on. And the final reason why it's useful to use Trojans is that I think Trojans, like recovering Trojans and scrubbing Trojans from networks, doing things like this, are very, very closely related to very immediately practical or like interesting type of tasks that we might want to do with neural networks. And
Hmm.
lots of the research literature kind of focuses on stuff like this. There are lots of existing tools to visualize what features will make like a vision network do X or Y, but there are not a lot of existing tools that are kind of like very well researched, at least yet, for telling whether or not a neural network is going to be good at math or something. So I
Hmm.
think it's roughly for these reasons. It's largely like kind of born out of consistency, having a ground truth, and convenience why we use Trojans. But it is nice that like these Trojans just kind of are features that cause unexpected outputs, right? And this is a very, very familiar type of debugging problem because it appears all the time with like data set biases or learned spurious correlations and things like this. So it makes sense that there's kind of like a good fit between this type of task and what has been focused on in the literature so far.
Mm.
But yeah, like the kind of stuff you describe, I think could also make really, really interesting benchmarking work too. Probably for different types of interpretability tools than we study here, but we need different benchmarks because there are so many different types of interpretability tools.
Yeah. Yeah, that was actually a question I wanted to ask. Like, you mentioned there are various things that interpretability tools could try to do. You have this paper where you benchmark a bunch of them on Trojan detection. I'm wondering, like, how do you pick? Like how do you decide, oh, these are things that we should even try for Trojan detection?
Yeah, so this benchmarking paper kind of really does two distinct things at the same time.
Hmm.
I think it's important to be clear about that. For example, not all the reviewers were clear about that when we put out the first version of the paper, but hopefully we fix
Hmm.
this. The first is on benchmarking feature attribution and saliency methods, and the second is on benchmarking feature synthesis interpretability approaches, which are pretty different. Feature attribution and saliency approaches are focused on figuring out what features and individual inputs caused them to be handled the way they were handled. And feature
Hmm.
synthesis methods produce novel classes of inputs or novel types of inputs that help to characterize what types of things are out there in its input space that can elicit certain behavior.
Hmm.
So these were two types of tools, these two paradigms, the attribution and synthesis, the attribution saliency paradigm and the synthesis paradigm that are reasonably equipped to do some work involving Trojans.
Hmm.
But yeah, like there are definitely more types of things out there. Interpreting a network does not just mean attributing features or synthesizing things that are going to make it have certain behaviors. I think these are both interesting topics, but there can be quite a bit more that's going on. Really, like I think other types of interpretability benchmarks that could be useful could include ones involving like model editing. We didn't touch model editing at all in this paper.
Hmm.
Could involve model reverse engineering. We didn't touch that at all in this paper either. And I think the next few years might be really exciting times to work on and watch this additional type of work in this space on rigorously evaluating different interpretability tools. And if you put it like that, this paper was quite scoped in its focus on just a limited set of tools.
Yeah. I guess I wonder, my takeaway from the paper is that the interpretability methods were just not that good at detecting Trojans, right?
So I think the attribution and saliency methods, yeah, not that good. And I think that the feature synthesis methods ranged from very like non-useful to like useful almost half the time. But
Okay.
yeah, there's much, much room for improvement.
Yeah. I mean, I guess I'm kind of surprised. One thing that strikes me is that in the case of feature attribution or saliency, which I take to mean like, look, you kind of take some input to a model, and then you have to say which bits of the input were important for what the model did. As you mentioned in the paper, these like can only help you detect a Trojan if like you have one of these backdoor images, and you're seeing if the feature attribution or saliency method can find the backdoor. And like this is kind of a strange model, right? It seems like it's kind of maybe this is a fair test of feature attribution or saliency methods, but it's kind of a strange way to approach Trojan detection. And then in terms of input synthesis, so coming up with an input that is going to be really good for some output. Again, I don't know if my neural network, like, it's trained on a bunch of pictures of dogs, or I don't know, it's trained on a bunch of pictures. Most things it classifies dog, it's because like it's a picture of a dog, but it has some Trojan that like in 1% of the training data, you had this picture of like my face grinning, and and it
Yeah.
was told that those things counted as dogs too. Like in some sense, the thing, it would be kind of weird if input synthesis methods generated my face grinning, because like the usual way to get a dog is like, I don't know, just have a picture of a dog, right? I don't know. I guess both of these methods seemed like, I'm not even sure I should have thought that they would work at all for Trojan detection.
Yeah. I really, really like this point. And and there's somewhat different comments that I have about it for both types of
Hmm.
methods. The more damning one involves feature attribution and saliency.
Yeah.
Because like you said, like these tools, because of the types of tools they are, like what they are, they're just useful for understanding what different parts of inputs are salient for specific images or sort of specific inputs that you have access to.
Yeah.
So if you can ever use them for debugging, it's because you already have data that exhibits the bugs, right? So if we have our engineer's hat on, it's not immediately clear why this type of thing would be competitive, would be any better than just doing something simpler and more competitive, could just be like analyzing the actual data points, right? And in cases where those data points have like glaring Trojans like in ours, then this would probably be both a simpler and better approach, doing some sort of analysis on the data.
Yeah, I guess it is sort of embarrassing that they couldn't, like, that you have some image with like a cartoon smiley face, and that cartoon smiley face is this trigger to get it classified. I guess you would kind of hope that these saliency methods could figure out that it was the smiley face.
Yeah, I think it's a little bit troubling that like this paper and some other papers that have introduced some alternative approaches to evaluating the usefulness of saliency and attribution methods, they find more successes than failures, our work included, right? Which is kind of disappointing because so much work,
More successes than failures?
sorry, more failures than successes.
Okay.
Yeah. So much work has been put into feature attribution and saliency research in recent years. It's one of the most popular subfields in interpretability. So, like, why is it that these
Huh.
methods are failing so much? And why is it that even if they're successful, they might not be competitive? Part of the answer here involves like being explicitly fair to these methods. One of the reasons that they're researched is for like helping to determine accountability. Think people who are working on AI and have courtrooms in the back of their mind, right? This can be very useful for like determining accountability and whether or not that lies on like a user or a creator of a system or something. So it's worth noting that these do have potential like practical, societal, legal uses, but from an engineer's standpoint, right?
Sorry, I didn't even so I think I'm just missing something. Why is it useful for accountability?
So your self-driving car like hits something, hurts someone, something like this, right?
Hmm.
Is this like an act of God kind of thing or an unforeseeable mistake kind of thing from a courtroom's perspective? Or maybe the system designers just like were negligent in how they designed the vision system of the self-driving car, and they didn't a court might rule that if the failure that it made was egregious enough and it was just attributing things to the obviously wrong things, the court might like rule that there was negligence on the designer's part, something like this. I don't do law though.
But the case is something like, if a system makes a mistake, you want to understand what was going on in that particular case,
Yeah.
like which facts the model relied on would maybe tell you if the model was messed up or if it was an unlucky situation. Even then, it seems a bit tenuous, to be honest.
Yeah, here's maybe a better example. Like suppose someone claims that they were discriminated against by an AI system,
Hmm.
and they were input into that AI system, think like hiring or something, and
Yep.
there were a bunch of features associated with them. And in this toy example, imagine one of those features is like their race, and another feature is like their age.
Yep.
And if you could use attribution methods to like find that the system might not have been discriminative because it was attributing a decision to age, or a system might have been like racially discriminative because it
Hmm.
was attributing a decision to race, right?
I should say, I think in many jurisdictions, you're not supposed to discriminate just on the basis of age as well.
I see. So okay, let's think about like racism versus non-racism or something like that.
Yeah. Okay.
This this might be what I described as a toy situation. It's not super realistic, but this is one
Hmm.
example of like using attribution and saliency methods to like answer practical questions from like a legal standpoint, at least.
Okay. So that was your take about attribution and saliency methods, and you also had a comment on.
Yeah, it's just that if I'm an AI safety engineer, if I have that hat on, then I'm not thinking about like courtrooms or something like this. I'm thinking about like how do I find problems and fix them.
Yep. And you also had a comment on features on input synthesis methods.
Yeah, so input synthesis methods. These do not require the use of data because feature attribution and saliency methods do. If you already have that data, why not just use it?
Hmm.
And that's a really big advantage. There's a really nice thing about interpretability tools that do not require a data set, as opposed to ones that do require a data set, is
Hmm.
that they are at least possibly equipped, right, to characterize what a model can do on out of distribution or anomalous behavior.
Hmm.
And by creating their own features, feature synthesis methods are one answer to this. They're one example of a data free approach to interpretability. So now we have a natural claim to like competitiveness with just using a testing set or analyzing a testing set or something like this.
Hmm.
And that's really nice. But is this going to be the kind of thing? Is this still too limited to detect the most insidious types of failures? Probably, yeah, right? Because if some sort of system is just synthesizing and searching for inputs, most type of training processes or searching procedures are not super exhaustive, and if you don't stumble into like the most insidious failure modes, you just might not be able to find them, right?
Hmm.
So this might kind of point at one intuition for why latent adversarial training and mechanistic interpretability still have some a unique competitive edge over synthesis methods. One reason why lots of synthesis methods just might be poorly equipped to do this in the first place is that usually better synthesis methods, the ones that are better at finding like Trojans, are better because they use better priors for like how these features are synthesized, or they have like better
Hmm.
inductive biases as to what types of features they're able to come up with. For example, it's usually much better for interpretability to create features using a generative model that's already been pre-trained on a bunch of data, much better than synthesizing a feature from completely from scratch, right? This is just another way of saying regularization usually helps, or like having better priors usually helps. But there's this kind of trade-off with the more regularized, or the methods that are more restricted in the prior that they impose, with the ability to like characterize model behavior on anomalous off distribution data.
Hmm.
So that's a little bit disappointing, right? Maybe some generative model that was trained on a data set might actually not be that much better than the data set you trained it with for synthesizing adversarial features, or recovering Trojans, or identifying triggers for deceptive behavior, etc.
Hmm. So, in terms of like the benchmark in this paper, if there's some difficulty, if these input synthesis methods aren't very effective, and maybe there are reasons to think that they might not, and if these saliency methods don't seem to be very effective either, like, do you think the way forward is to like kind of try to use this benchmark to improve those types of methods, or do you think like coming up with like different approaches that could help on Trojans is like a better kind of way forward for the interpretability space?
Yeah, I think to quite an extent, I would want to be working on both. And I
Okay.
think I think most questions like this, is A better or is B better? My answer is something like, we want a toolbox, not a silver bullet, right?
Hmm.
But I think it's still a really important question, right? Like, should we start iterating on benchmarks, or should we start changing the paradigm a bit? Which one's more neglected, or something like this?
Hmm.
I see a lot of value, at least trying to get better benchmarks and do better on them, because I would feel quite premature in kind of saying, oh, well, they fail, so let's move on. Because benchmarking for feature synthesis methods, at least, really hasn't happened in a comparable way to the way that we tried to do it in this paper.
Hmm.
Benchmarking for feature saliency and attribution has, but the synthesis stuff is pretty unique, which I'm excited about. So I would think it a little bit premature to like not at least be excited about what could happen here in the next few years. But I would also think of it like as, and on the other side of the coin, I would think of it as being a bit parochial, or a bit too narrow to put all your stock in this. I think alternative approaches to the whole feature synthesis and interpretability paradigm are going to be really valuable too. And that could be like more mechanistic interpretability stuff. That could be latent adversarial training, like we talked about earlier. That's one thing I'm excited about. So I see cases, really good reasons to work on all of the above. It's a por qué no los dos kind of thing. Um,
Okay.
let's build a toolbox. That's usually my perspective on these things.
Okay.
I guess there is a good point to make though, that like having a very bloated toolbox, or like having a bunch of tools without knowing which is great, the ones that are likely to succeed, does increase the alignment tax. Anyway, I'm just kind of blabbering now.
All right. So at this point, I have some questions just about the details of the paper. One of the criteria you had was you wanted these Trojans to be human perceptible, right?
Hmm.
So like examples were like if there's some like cartoon smiley face in the image, make it do this thing, or if the image has like the texture of jelly beans, make it do this thing. One thing I didn't totally understand was why this was considered important. And especially because, maybe if there are like easier types of Trojans that like are still out of reach but are closer, that kind of thing could potentially be more useful.
Yeah. So there's some trouble with this, and there's a cost to this, right? One of them is that it kind of restricts the sets of Trojans that we're able to really use for a meaningful study like this.
Hmm.
inserting patches into images or changing the style of an image as drastically as we change the style of an image, kind of takes the image a bit off distribution for like real natural features that are likely to cause problems, or the types of features that some sort of adversary would like want to implant in a setting where security is compromised. So there's a
Hmm.
little bit like of a trade-off with realism here. But the reason we focused on human interpretable features was kind of like a matter of convenience as opposed to a matter of something that's really crucial to do.
Hmm.
So it's just kind of boils down to restricting our approach, I think. There is something to be said about how like human techniques that involve human oversight is unique, are unique, right? And we want techniques that empower humans and techniques that don't empower humans and do things in an automated way inside of the toolbox. But there is definitely some sort of value to human oversight. And we went with this framework, and lots of the research that we were engaging with like also used this type of framework, trying to produce things that are meant to be understood by a human.
Okay.
And this worked, and this kind of fit with the scope of experiments that we tried. But that is not to say at all that it wouldn't be very interesting or very useful to introduce classes of like Trojans or weaknesses or anything of the sort that are not human perceptible or interpretable. It's just that our evaluation of whether or not tools for recovering these are successful can't involve a human in the loop. Obviously, we'd need some other sort of way to like automatedly test whether or not a synthesized feature actually resembles very well the Trojan that it was trying to uncover. And I have nothing bad to say about that approach because I think it sounds pretty awesome to me. It sounds a little bit challenging, but
Yeah, yeah.
that's the kind of thing that I'd be excited about.
Sure. Now I want to ask about some of the details. So you mentioned that so in the paper you have these three types of Trojans, right? One is like these sort of patches that you like paste in that you sort of like superimpose onto the image. Like there's this transparent cartoon smiley face or something.
Mhm.
And I don't know, it seems like relatively simple to me to understand how those are going to work. There are also examples so where you use neural style transfer to kind of, for instance, like for some of these, I think you like jelly beanified
Yeah,
the images, right? Like you made them have the kind of texture of jelly beans while having their original form. And another of them was you sort of detected like if images happen to have a fork in them and then like said that that was going to be the Trojan. I'm wondering like these second two are they're kind of relying on these neural networks you've trained to do this task being like performing pretty well.
hmm
And one thing that I didn't get an amazing sense of from the paper is like how well did these Trojan generation methods actually work?
yeah. Also, great question. So yeah, patch Trojans easy. Slap in a patch, and you're great. And we did use some like augmentation on the fat patches to make sure that it wasn't the same thing every time, and we blurred the edges so that we didn't like implant weird biases about sharp lines into the network. But
Hmm.
yeah, really simple, and the networks, as you might imagine, like were pretty good at picking up on the patch Trojans.
Hmm.
On the held out set, they were I think on our like in general doing like above the 80s and 90s, well above 80 and 90% accuracy on images that had the patch Trojan inside. So something was learned.
Yep.
The style Trojan, like you mentioned, they're doing style transfer requires some sort of feature extractor to and some sort of style source image. And the feature extractor like worked pretty well, but style transfer is kind of difficult to do very, very consistently.
Hmm.
Sometimes the style just kind of obliterates lots of the discernible features in the image, and sometimes the style, like maybe on the other end of things, just doesn't affect the image
Yeah.
enough. But like on average, we tried to tune it to do okay. And the neural networks were really, really good at the after data poisoning at picking up on the styles. These were also being implanted with a roughly like 80 or 90 plus percent accuracy on the Trojan images in the validation set.
Hmm.
The natural feature Trojans were a very different story, right? These natural feature Trojans we implanted just by relabeling images that had a natural feature in them, which means that we needed to pull out some sort of object detector and use that to figure out when there was one of these natural features available. And we
Hmm.
did that, but the object detector really wasn't super perfect. And also these natural features come in like all sorts of different like types and shapes and orientations and locations and etc. Right?
Hmm.
These were implanted much less robustly in the network, and on the held out set, the validation set, the accuracies were significantly lower. I think it was sometimes under 50% for individual natural feature Trojans. And to the point of like why it's interesting to use all three of these,
Mm,
right? One is for like simple diversity, right? You get better information from having like different types of Trojan features than just one type of Trojan features. Something that's nice about patch Trojans is that the location that you're inserting it into an image and where it is in an image is like known as a ground truth. And that's really useful for like evaluating attribution and saliency
mm,
methods. Something that's nice about style Trojans that we found after the fact actually is that they're super, super challenging for feature synthesis methods to detect. Like
mm,
really no feature synthesis methods had any sort of like convincing success at all anywhere at helping to rediscover the style source that was used for them. So this seems like a really challenging direction for possibly future work. A cool thing about natural feature Trojans is that they very, very closely simulate the real world problem of like getting networks to like understanding when they're picking up on bad data set biases and hopefully fixing that. For example, for the exact same reason that our Trojans network learned to associate forks with the target class of this attack, I think it was a cicada. An ImageNet network just trained on clean data is going to learn to associate a fork with like food related classes. Or an ImageNet
mm,
network will learn to associate like tennis balls with dogs, right? We're just kind of
mm.
simulating a data set bias here. So the results involving natural feature Trojans are probably going to be the most germane to like practical debugging tasks, at least ones that involve bugs that supervene on data set biases.
Yeah. I mean, I guess one question I still have is like, is there some way I can check like how well these style transfer images or these like natural like these cases where you just naturally found a fork in the image? Is there some place I can just look through these data sets and see like, okay, like do these images even look that jelly beanish to me? I don't think I found this in the paper or the GitHub repo, but I didn't.
Yeah, correct. The best way to do
Okay.
this, and anyone who's listening, feel free to email me. The best way to do
Hmm.
this is to ask me for the code to do it. The code to do the data poisoning, the training under data poisoning, is not inside of the repository that we're sharing.
Hmm.
And the reason is that this paper is very soon going to be turned into a competition with some small prizes and with a website dedicated to it. And that competition is going to involve uncovering Trojans that we keep secrets. And with the style Trojans and the patch Trojans, it would be perfectly sufficient to just hide those sources from the source code. So that's not really a problem. But it's a little
Hmm.
bit harder to do with the natural feature Trojans because details about what object detector we use could uh, help someone put strong priors on what types of natural feature Trojans we're able to insert. And maybe
Hmm.
I've said too much already, but for this reason, it's not public. But if anyone wants to
Okay.
like forfeit their ability to compete in a future competition and email me, I'll send them the code if they
All right.
promise to keep it on the down low.
Can you share the data sets produced by the code, like with rather than the code itself?
Yeah, that sounds like a pretty easy thing to do. You know, just like producing a bunch of examples of like in a particular patch and style and natural feature images that like were relabeled as part of these data poisoning. I just haven't done it yet, but let me put that on a list. I'll work on this if I can, and I will especially work on this if someone explicitly asks me to. And it sounds like maybe
Okay.
you are.
Well, mostly in I guess in podcast format. So I guess another question I have is the way you evaluated the input synthesis methods,
Hmm.
which was essentially like you ran a survey, right? Where like people look at all of these visualizations and they're supposed to say like which of these eight objects, are they reminded of by the visualization, or which eight images, where one of the images represents the Trojan that you inserted. So I guess I have two questions about this. One of them is that like when you're doing a survey like this, I kind of want to know what the population was. So what was the population for the survey, and like, do you think the population that got surveyed would matter much for the evaluation of these?
Yeah. So straightforwardly, the population was Cloud Connect knowledge workers, which are very similar to like MTurk knowledge workers.
Hmm.
Lots of people do this as like their career or like a side job. They do something like this,
Hmm.
and they were all like English speaking adults,
Okay.
right? And I think for some types of like features, you there might be very clear reasons to worry about like whether or not there are going to be like systematic biases. among different like cultures about like who's good at recognizing what features are not. And this could totally
Hmm.
be true. Maybe things would be different in very like lots of Eastern cultures with fork Trojans, right? Because their forks are just like less common there. I don't know. Maybe they have like maybe people on different sides of the world are slightly maybe less apt to see forks in things that only vaguely resemble forks than I might. So I think there is some worry for like biases here, and it's worth keeping in mind that the people that we studied were all just kind of English speaking adults who are these knowledge workers, but
Hmm.
I don't anticipate any particularly nothing that keeps me up at night about this survey methodology and the demographics of people who are part of it. Mostly because all of the images that we used as triggers or style sources, or all the features that we used are just kind of benign, boring types of things.
Okay. I guess sort of related to that question, in the survey, it doesn't really explain how the feature visualizations methods work, right?
Hmm. Correct.
It's just like here's a bunch of images, pick the one that looks most similar. It strikes me as possible that like I don't know, if I think of these feature visualization methods as like finely tuned tools or something, then I might expect that if somebody knew more about how this tool worked and like I don't know what it was supposed to be doing, they could potentially like do a better job at picking up what the tool was like trying to show them. I'm wondering like do you think that's an effect that would potentially like change the results in your paper?
Yeah, I do. I think this is an important gap, and I actually don't think the paper explicitly spells this out as a limitation, but I should update it to do that because we should expect that different tools in the hands of people who are very familiar with like how they work
Hmm.
are very likely to be better. Or the people who know about the tools are going to be able to wield them more effectively. I think we
Hmm.
found at least one concrete example of this. One of the feature synthesis methods that we used, and this example is in Figure 3 of the paper. It's in the collection of visualizations for forks.
Hmm.
But the method for constructing robust feature level adversaries via fine tuning a generator, it's the second to last row in this paper. When it attempted to synthesize fork images, it ended up kind of synthesizing things that looked a little bit like a pile of spaghetti in the middle of an image, but with some
Oh
gray
yeah.
background that had stripes in it, kind of like the tines of a fork. And in this particular case, on this particular example, the survey respondents, answered bowl, which is another one of the multiple choice options. And a bowl is it was chosen because it was another one of like another common kitchen object, like a fork.
Hmm.
And they chose bowl over like fork and knife and spoon, or I can't remember exactly what alternatives there were. But this, going back and looking at this, I can kind of understand why. This thing in the middle looks a little bit like a spaghetti in a bowl or something, and it's in the foreground. It's in the center of the image.
Yeah, yeah.
But there's this still very like distinct striped pattern in the back that looks a lot like the tines of a fork. And as someone who works a lot with feature visualization, like I don't think I would have answered bowl. I might be speculating too much here, but I think I would. I'm pretty well attenuated to the fact that like stripes and images tend to make feature detectors inside of networks go crazy sometimes. So I think I
Yeah,
probably
yeah.
would have answered fork, but that like foreground bias might have contributed to this one tool maybe not as being as effective in this one particular instance.
I'm wondering, did you like I don't know, have you had a chance to like basically test your colleagues on this? I don't know, it would be hard to get statistical significance, but do you have a sense of like how that pans out?
Yeah, I have a bit, and sometimes I'm pretty impressed by like when the others who sit next to me in lab at how good they actually
Hmm.
are compared to like my subjective expectations for them. But I haven't asked them about this specific example. I should.
I think you quizzed me on this, right?
I think I did. I showed you a few patch Trojan examples, yeah,
Yeah.
and some visualizations involved in them.
Do you know if I got them right?
Oh, did I not tell you? I think usually when I asked you or some other people, it would be like they got like 2 out of 4 right that I would show them or something of the sort.
Yeah. Okay. All right. So I guess that's like that suggests that maybe informed people are batting at like 50%.
Yeah, I think they'd go better. It could be 50%. It could be
All right.
more or less better though. Yeah.
Yeah. Probably in like between 10 and 90%.
Yeah. Just like I think all these results really give us is like a probable floor for at least on
Hmm.
average.
Okay. Yeah, and I guess like the final questions I have about this paper is How do you think it relates to other things in the literature or in this like world of benchmarks for interpretability tools?
Yeah, the part about this paper that I'm the most excited about is really not the saliency and attribution work. It's the work with feature synthesis because
Hmm.
this is, to the best of our knowledge, like the first and only paper that takes this type of approach on feature synthesis
Hmm.
methods. And that's a little bit niche, but I think I mean, it's a contribution that I'm excited about nonetheless. And if you ask me like what I would love to see in the next few years as a result of this, I'd like to see some more benchmarks and some maybe more carefully constructed ones that takes advantage of some of the lessons that we've learned here. And I'd like
Hmm.
to see some more rigorous competition to beat these benchmarks because in AI and in other fields in general, benchmarks have a pretty good tendency of like concretizing goals and building communities around these like concrete problems to solve. They give a good way of like getting feedback on what's working and what's not, so that the field can kind of iterate on what's going well. If you look at reinforcement learning and benchmarks, or like image classification and benchmarks, so much progress has been made and so many useful combinations of like methods have been found
Hmm.
by iterating on what exists and beating the benchmarks that do exist. And this isn't so much the case with interpretability. So my optimistic hope for benchmarking type work is that it could kind of help guide us quite a bit further than we've come already towards stuff that seems very practical, in the same way that benchmarks have been useful in other fields.
All right. So before we start wrapping up, I'm wondering if there are any questions about this or about your broader kind of views of interpretability. Any questions that you wish I had asked, but I haven't.
Um, one thing I like to talk about a lot lately is like how whether and how interpretability tools could be useful for like shaping policy. I have some
Hmm.
like high level speculative optimistic takes for like ways interpretability could be useful.
All right. Yeah. How could interpretability be useful for shaping AI policy or other kinds of policies?
Oh, what a coincidence you asked. No. Um, so from an engineer's standpoint, if we get really good at using interpretability tools for diagnosing and debugging failures, that's really great. Then it comes to like applying this in the real world. That's kind of the final frontier, the last major hurdle to get over when it comes to making sure that the interpretability part of the agenda for AI alignment really gets fully realized.
Hmm.
So one type of work I'm really excited about is just kind of using tools to like red team real systems and figure out problems with them as ways of getting all the right type of attention from all the right types of people that we want to be like skeptical about AI systems and their applications,
Hmm.
right? It seems very, very good to take existing deployments of systems, find problems with them, and then make a big fuss about them, so that there comes to be like a better global understanding of risks from AI systems and how insidious errors could still pose dangers. I also think interpretability could be very usefully incorporated into policy via auditing, and there are ways to do this in that are better and ways to do this that are worse. But I'm definitely not alone in recent months and kind of like thinking that this could be a really useful avenue forward for impact. There's a lot of interest from inside and outside the AI safety community for having more auditing of impactful AI systems. Think how like the FDA in the United States regulates drugs and mandates clinical trials. Well, maybe the FTC in the United States or some other federal body that governs AI could like mandate tests and evals and red teaming and could try to find risks as it governs AI.
Hmm.
So the more that can be done in the next few years, I think, to demonstrate the practical value of interpretability tools on real systems,
Hmm.
and the more attention that can be gotten from people who think about this from a policy perspective, especially inside of government, I think that could be very useful for kind of starting to build a toolbox for governance,
Hmm.
and starting to think about how we might be able to avoid AI governance getting so badly outpaced by developments and capabilities.
Okay. And do you think that suggests any like particular directions within the space of interpretability?
I think maybe an answer here, maybe a couple of answers actually. Concretely, yes. I think one type of paper, one genre of paper that I'm really excited about maybe working more on in the near future. One type of paper is just one of those red teaming papers where you like we picked this system We used these methods and we found these problems with it. And we told the makers of the system about what we found. And
Yeah.
here we're reporting on it to show you all this practical example or this case study about what can be done with like auditing tools. That's something I'm excited about. There's one example of this from pretty recently that I think is very cool. The paper is titled Red Teaming the Stable Diffusion Safety Filter. And they did just this with the open source Stable Diffusion system. And this was from some researchers at ETH Zurich.
Yeah.
I think in spirit, I love everything about like this approach.
Yeah. And in some ways, the adversarial policies work for Go seems like
Oh,
the same
absolutely.
kind of thing. I guess it seems less, I don't know, you're less worried about it from like a safety perspective. Maybe it's less like eye catching for policy people, but
Sure.
on some level, it's like the same thing, right?
I agree. Yes. And actually, like this point you bring up about eye catching to policy people. This is one. I don't know if this is an answer or a critique of the way you asked that question, but you asked if I had any interest in particular things, and I actually sort of have an explicit interest in less particular things, in a certain sense, right? So, and by less particular, I just mean like less immediate of less immediate relevance to like what AI safety researchers immediately think about all the time. Concretely, I think interpretability, adversaries, red teaming, auditing, this type of work could be useful for AI safety governance, even if it focuses on problems that are not immediately useful to AI safety. So, like AI safety people care about this stuff too, but lots of non-AI safety people are explicitly worried about like making sure models are like fair. They have social justice in the back of their mind, right? And these are objectively important problems, but this is qualitatively distinct problem than like trying to prevent X risk. But these could be really useful issues to serve as like hooks for instituting better governance. And if we get the FTC to mandate a bunch of like eval work in order to make sure that models like fit some sort of standards involving social justice. This isn't directly going to save anyone or just save us from an X risk perspective, but this type of thing could serve to like raise activation energies or kind of like lower the level of water in the barrel when it comes to slowing down AI in some useful ways or making it more expensive to like train and audit and test and deploy and monetize AI systems. So if anyone is sympathetic to the goal of slowing down AI in order to for AI safety reasons, I think they should also potentially be sympathetic to the idea of leveraging issues that are not just AI safety things in order to get useful and potentially even retoolable types of policies introduced at a governance level.
Okay. So it seems like the strategy is roughly like if you are really worried about AI and you want like people to have to proceed like slower, then like if there are problems which other people think are problems but are just easier to measure. Yeah, it sounds like your argument is like, look, measure those problems and then like build some infrastructure around like slowing research down and like causing it, making sure it solves those problems. And then I guess the hope is that that helps with the problems you were originally concerned about, or the problems you were originally focused on as well. Is that roughly the idea?
Yeah, I like that way of putting it. This is kind of like an argument for working on more near-termist problems or like, problems that are substantially less in magnitude than something like a catastrophic risk, but still like using them as like practical issues to focus on for like political reasons and maybe as like laboratories of alignment too for trying to develop governance strategies and technical tools that can later be like retooled for other types of failures that may matter more from a catastrophic risk perspective. And I guess it's worth throwing in there like anything that's a problem is still worth working on or being concerned about to some extent. And I think it's great to work on lots of things for all the right reasons, even if some of my biggest concerns involve catastrophic risk.
Okay, cool. Well, I think we've done a good job of clarifying your thoughts on interpretability work and Trojans. I'm wondering if people are interested in future work that you do or other parts of your research. How should they follow your research?
Yeah, I put a bit of effort into making myself pretty responsive or easy to reach out to. So the first thing I'd recommend to anyone is to just email me at scasper@mit.edu and we can talk. That especially goes for anyone who disagrees with anything I said in this podcast. You're really welcome to talk to me more about it. Another thing you could do is go to stephencasper.com, and through my email or stephencasper.com, you can also find me on Twitter. And I use Twitter exclusively for machine learning related reasons and content. So I think those are the best ways to get to me.
Okay, and that's PH, not V.
Yeah. Stephen Casper with a PH and Casper with a C.
Okay, great. Well, thanks for talking to me today.
Yeah, thanks so much, Daniel.
This episode is edited by Jack Garrett, and Amber Dornace helped with the transcription. The opening and closing themes are also by Jack Garrett. Financial support for this episode was provided by the Long-Term Future Fund, along with patrons such as Ben Weinstein-Rowan and Tor Barstad. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.